So yeah, as Rosaria stated, I'm working at the University of Applied Science in Western Switzerland. So it's the French part of Switzerland, as you can figure out with my accent. So the story started with a guy who's taking care of elderly people, and they are trying to keep them at home, and people are falling down, and he told me, yeah, we are not able to find a real solution that we can develop and deploy. And so I said, okay, let's try to do some stuff with that. And I had a student in master who made his master thesis, and I'm working in computer science, so people are able to do some code, but they are not specialists in data mining. So I decided to use Knime so that we can go pretty quickly to the goal and try to solve the problem. So let's see how we can do that with Knime. So let's try to follow the path that Knime gives us to try to go from the problem to the solution and to deploy it. First, what we had a recording from Android watches. There's two kinds of Android watches, and as you can see there, we have a lot of variables coming out from these watches. But what we are using, and what a lot of people are using now, it's mainly the linear acceleration. So the linear accelerations are, the acceleration you have on all the three axes of your device, and the linear acceleration are just, balancing the gravity and the position. So we have something like a clean signal coming out of the watches. So that would be our input signal. Looking at the literature and making the first steps, we have figured out that using the three acceleration on the three axes was not a good idea. So what we did, we use, sorry, there is some geometry there. We use the norm of the vector, in fact, so that we have something that is a value that is growing and going down, like in time. So it's simpler. Instead of having three values in three different directions, which can be troublesome, we use only the magnitude of the vector. Okay? So now, what is a fall? That was the question also. Of course, if you fall down, like you trip down from stairs, so it's what we call a hard fall, this is pretty easy to detect, because you put a threshold, and then if you are up at the threshold, then you can detect it, and you go down like that, and then you detect it. So with this kind of falls, like hard falls, you have something like 98% of detection using a simple threshold. Okay, so problem solved. But now, if you go to soft falls, which is the problem with elderly people, is that they are sleeping down the chair, the bed, or maybe not that one, but the other one. So it's something that is a problem, because if you look at the signal, so then the signal is something like that. And if you look at, in comparison, a normal activity, then it starts to be a little bit more difficult to distinguish between the two. So now we figured out that we have to go a little bit further and try to do what I was using to do when I was younger, which is signal processing and things like that. So the detection with the threshold in this case was only 1%. In fact, we cannot detect anything. So thinking about the signal, I used something that is widely used in different areas, for example, in speech, where we can, in fact, try to find patterns in a signal. And to do that, we use temporal, so that the patterns, in fact, you have the full signal going there. And what we can do, we can apply some transformations and try to decompose your signal in different parts. And this particular one is called FFT, so fast Fourier transform. So I give up the equations, but basically by using decomposition of sinus waves, you can recompose any signal. So for us, we will have coefficients. I mean, we will have the coefficients of every of these signs, and this will give us values that will be the part of the signal. And of course, as we are in a discrete world, because we are doing computers, so we are sampling things, just the name is a little bit different, what we call a discrete Fourier transform. It's the same thing, okay? Now, how do you integrate this with Knime? So first, we did some pre-processing thing. So we have the samples. We try to do this magnitude vector thing. And so we put it in a table. So that we have this as the input of our system. And so let's have a look at what's going on there. So we have this FFT 1D, which is 1 dimension, because we have a temporal signal, so it's a 1-dimension thing, it's not an image. So what do we have into that? We have some pre-processing to create collections. Then we have a Java snippet and something to recreate, to split the collection. This is just internal thing. We have these marvelous nodes that we have seen yesterday and also a little bit this morning, which are able to give us some constants that we can preset values for our system. And we have this Java snippet, which is one of the first very interesting nodes that was not directly doing something precise in Knime. So with this Java snippet, in fact, you can add your own knowledge into it. And so I choose to use this Java thing because first, Knime is written in Java, so everything you use, every code you build in Java will be very quickly executed. So now if we go to the internal of the Java itself, so now there is some code, don't be afraid. I will just tell you and show you what is important there. So in this code, basically, as you can see, there are not a lot of lines. And in these lines, they are just basically using a library there that is an open source library. We will come back to that just later. And in this library, we'll just take out what we need. In this case, it was the discrete Fourier transform. And do some just take out the value from the table that we have as input, put them in a nice array in a way that we can use it with our library, then do the job here. The job is done just here, just one line. And then put it back in a way that Knime can understand the array and then come out of the node. Okay? So the library that I've used is an open source library, gwave.jar, that was written by someone at the MIT, Mr. Schieblich at MIT. And so you can have the source, I put it as a reference, you can have the source code, and you can have also the description of what it's doing very quickly. And so it's pretty useful and straightforward. It's license-free, so you can reuse it and publish your nodes with that without any problems. Now, I figured out that as we had done this detection with fast Fourier transform, the Gwave library has many possibilities. And there are other possibilities that I also wanted to explore, which one of them was the wavelets. So we have, it's a very popular also way to detect patterns in an image or in the signal. It's using, as you can see here, an example of detecting edges in a picture using what we call wavelets. We'll not discuss about the detail of the property of the wavelets, but just to let you know that these three kind of wavelets that basically are some small signal that you apply to your own signal, and then you get out some parameters and some features, and depending on the form of the wavelet that you use, you will get other parameters. And this allows you to get and take out very interesting information out of that. Okay, so it's very popular in image processing and also in signal processing. Okay, so I've done this also, so basically built a node with this wavelet capabilities. And as you can see, it's really close to the other one, so I use also the Java snippet. What is a little bit different here is in the constants is that I can choose the wavelet type as a constant, so as a table that you can choose values. And if we look into the code itself, basically it's the same than before. We use the same library, just say that you want to use wavelets. We just make a case here to choose the wavelets. So thanks to the node with the table. First, we can choose very easily the wavelets, and then it's the same thing, the same code there. Okay, so a pretty straightforward implementation. Okay, now so that I've pre-processed my signal, the idea was now to analyze it. Okay, I would say analyze. So classification and experiments are pretty classical. You know, I guess everybody here, or almost everybody here, knows how to use that. So we have the classical input data, then do experiments, then scoring. So for the input data, we just take out the table that we have created coming out either from the FFT or from the wavelets. We do some filtering here to be able to choose the proper columns, because we can choose more or less coefficients if we want. We split the input data in two parts, one for the training, the other one for the test, and we have put in parallel many different algorithms to see how they perform. So using the same data as input and output. We also use a little bootstrapping part here, which is when you do learning, what you would like to have to be sure that your algorithms are performing properly is to balance the data set. So this bootstrapping here is balancing the data, adding some more, copying some more input data, and be sure that we have a balanced data set. Then we do a little combination here, which is combining all the output of all the system. We use X-partitioner, which makes us more statistical, I would say. So because we do many experiments, and so the results that you obtain are done on many loops that we do. And at the end, so what we have here, we have also a scoring. And we get out some information and some result out of that. So what are the results now? First, what we used here, as we have two categories, and the two categories are I'm performing a soft fall, or I'm doing something else. And so we use these two categories and try to separate them. So basically what we do here, we use the ROC curve, and it's also a well-known scoring method. So we use, in fact, the surface under the curve, AUC. And we are comparing these surfaces. So the larger the surface is, the better is the results. And so 1 would be the better, and 0.5 would be the worst. And then if you look at the results, then you can see that, okay, these are the three different the three best different pre-processing that I've used. So fast Fourier transform with 8 coefficients, the wavelets, the array one, the square one, and the Dobeishi with 128 coefficients. So you can see that with this processing, the two best algorithms are, for this one, the Decision Tree Ensemble, and then the Decision Tree Ensemble. On the three different pre-processing, it's always the Decision Tree Ensemble that is the best. You can see that the others are different. So we have here MLP, so neural nets, that comes out. We use it because it's very popular also, and people use it. It's never the first, but still, as a comparison, it's always very important, because we can find in the literature that people use that, and they were very happy with it. But let's say that the decision tree are always performing the best. And so I've added something called here the precision, because very often when we see a result with AUC, you see only the AUC, but you don't see the precision. The precision here is very important, because this means that, in fact, between 0.484 and 0.87, there's no difference. It's not relevant, because the precision is 0.03. So basically all the three scores here are the same. That's what it means if you use the precision. And so I figured out that this was missing, in fact, in Knime. So this way of computing the precision. That's why we added this node here, scoring. And if you look at inside this scoring node, as I'm a fan of Java, I used also Java snippet again. And basically, in this Java snippet, we are performing the computation that is using computing the precision. And this is from a well-known paper dated in 1982 that shows how to do it, how to compute this precision properly. Okay, so the thing is that now we checked different ways to process the signal. So we know that if we use either FFT or wavelets, we have good results using Decision Tree Ensemble. And then finally, I asked myself, say, okay, what if I don't do any pre-processing, and I use only the magnitude vectors, which is the input signal, without doing anything, and I try to put it in the Decision Tree Ensemble and see what's going on there. And surprisingly, the results are pretty good. So 8.5. So if you look at the precision again, then this means that it performs as good as if you use fast Fourier transform or wavelets. This is very interesting as conclusion. This means that your Decision Tree Ensemble can do pattern recognition. So it can learn patterns directly without doing pre-processing. And that's pretty impressive. And it's something that we find everywhere now. We process different kind of signals, multidimensional also. If you know how to handle properly this Decision Tree Ensemble, then that's definitely the best argument you can find nowadays, at least in Knime. Okay? So that was a pretty funny conclusion, because what's below that, it means that, in fact, if I think about what we will do now, which is integrating and deploying something in an Android device, then the computation power is important. Still, okay, we have some more computation power now in this micro device that we had before, but still we have to perform this every 2 or 3 seconds and perform all the transformation. So if we can remove some useless transformation, then it's good. So this will simplify our process, and so simplify also the code and the maintenance and all these kind of things. So then, okay, now we have our model that we have here. So we have found our best model. So now I'm switching to PMML. So that was pretty straightforward. So we have the process. We know that we can obtain good results. We have the data. So let's now use the PMML version of the Tree Ensemble Learner. And then using that, we have what we have done at that time was to have this model extraction here and create a PMML file that can be used after that directly on the Java code on the Android app. Okay, so we used a GPMML open source library to do that. Basically, this GPMML library is able to run on Android, and so we could port it directly on Android with that. The thing is that, if you were there yesterday, we have now some new feature that is called the PMML compiler that will create directly a jar file, so directly a Java code. So we didn't try that yet, but of course we will. I think as it was advertised yesterday, it should do a more compact code, a faster code, so we are really dying to try this as soon as possible. Okay, so now if you look, so what we have done there was that we had already some applications running on Android apps. So the people who designed this at that time already had recorded information using thresholds. And so what we had to do there is to add our own system to the existing app. And that's what we have done here. It's pretty simple, I have to say. So basically, we here in the capture data analysis PMML evaluator here, we have our Knime workflow, which is now on the PMML form, and just basically detecting if there is a fall or there is no soft fall or not. And then we have all the rest of the application that will notify the user, send the information to an emergency system, and make it work, in the reality. So that's it for the implementation. What I think is that we should, of course, enhance our system now. We have this PMML to Java compiler that is pretty well done, and I will be very interesting to test it. We also have now, with the last version of Knime, also these wrapped nodes. So this means that we will be able to wrap down all the parts using the Java snippet and all the preparation of the preprocessing, and so the fast Fourier transform and the wavelets. And I guess we will package this as a black box, so with some input parameters. And yeah, we will provide you this, I guess, after the meeting, once it's done. We have done some packaging so you can use it and try it for yourself. The thing also is that we would like to optimize the size of the PMML in memory. It's very important for us because it's a large memory. Now we use a lot of memory. And so we have a lot of things to try to, at first, reduce the decision tree ensemble itself and see what we can, optimize in a way that we go down in the size. Okay, just some references. Of course, as I told you, we will provide some example workflows, so where you have all the preparation. So basically, you will have the pre-processing part and the testing part, and so you can try it by yourself. And just to let you know that we wrote a paper on that application, which will be presented in Crans-Montana, which is a very well-known ski resort close to the place where I live and where we have the school. So you're welcome there if you want. And okay, so maybe what I would like to point out here is that it is possible to very quickly deploy an application on a lot of different devices very quickly and without having deep knowledge in either data mining or signal processing. So the student that I had there learned things in 3 or 4 months and was able to do an application that was working, which is for me extremely important because that's the way to spread things pretty quickly. So that's it for me.